First of all, I wish to thank the organizers for this opportunity to present this work here. So let me first give an overview of what this remodeling conjecture is about. So this can be viewed as some version of mirror symmetry. So broadly speaking, mirror symmetry relates the A model on some symplectic manifold to the B model on some mirror manifold defined in terms of the complex structure of the mirror manifold. Today, the A model we will consider is very special. It's a symplectic toric Calabi-Yau 3 manifold or 3 orbifold, where this omega is the symplectic structure. And here, for this kind of target, there is an explicit construction of mirror given by Hori-Vafa. And so it is of the following form: UV minus H capital X capital Y is 0, where UV are in C and XY are in C star. So this is a non-compact Calabi-Yau 3-fold, and omega is a very explicit holomorphic 3 form. And this is a Laurent polynomial described explicitly in terms of the toric data. There are many aspects of mirror symmetry, for example, homological mirror symmetry, but I'm interested in topological strings. So for A model topological string, they are Gromov-Witten invariants, which you have already seen several times in this conference. So we will consider this. Okay. Yeah, so these are Gromov-Witten invariants. So this is generating function of genus G Gromov-Witten invariants. They count holomorphic curves of genus G in the target X. We will also consider open Gromov-Witten invariants. Where L is some Lagrangian submanifold of this target, and we count holomorphic curves with G handles and N holes with boundary in this Lagrangian submanifold. So now for the B model side, so we know that there's this BCOV. They have, let me. Yeah, so for like compact Calabi-Yau 3-fold, this is very difficult, and there's a holomorphic limit, which is supposed to correspond to this under the mirror map. But then the good news is for this toric case, this theory can be reduced to the theory on this mirror curve. So let me just say where C is just this defined by this affine plane curve. Of course, this is not well defined on C star, but later we can make sense of this. So then on this mirror curve, there are
I'm sorry, what is BCO?
project. Yeah. Oh, thank you. So yes. So then, right. So on here, there are. So yeah, well, so these are the formulas, but I will say more later. So the good news is that this is defined purely in like classical complex one variable of this Riemann surface. So it's very classical. It's defined in terms of like 19th century mathematics. Okay, so then this remodeling conjecture. Oh, and so it is conjecture that actually there is also formula to omega G0. So G0 is supposed to be this thing. Yeah, I'm not. Okay, so what is this? This is so this is due to BKMP, where B is Bouchard, K is Klemm, M is Marino, and P is Pasquetti. So their conjecture says under mirror symmetry, this should correspond to omega G0. So this can be viewed as an O-genus closed mirror symmetry. This is a version of O-genus open mirror symmetry. And this has, so Eynard-Orantin proved this when X is a smooth toric symplectic manifold. And my collaborator, Bohan, Fang, and Zong, and myself, we did the orbifold case. Okay, so that's what this conjecture is about. But I would like to spend maybe 20 minutes to explain like the Gromov-Witten theory and open Gromov-Witten theory of toric Calabi-Yau threefolds. Yeah, so I will come back to this later. It's defined in terms of omega G1, and omega Gn is defined recursively. But we will come back to this board later. So first, Gromov-Witten invariance of a smooth toric Calabi-Yau threefold. So X is smooth toric Calabi-Yau threefold is a smooth complex variety of dimension 3. Canonical divisor is trivial, and there's a algebraic torus is open dense subset such the action of T extends to X. And then in this case, so let's assume that this has at least one fixed point. Then we can consider the so-called Calabi-Yau torus, which acts trivially on the canonical line bundle. So this toric Calabi-Yau threefold is never compact. So in order to define this invariance, we use equivariant localization. So we define actually, so this is the genus G degree D Gromov-Witten invariance. You take the stable map from genus G curve in degree D. D is some curve class. Yeah, so this is the virtual normal bundle of this fixed point. So this is the virtual normal bundle of this torus fixed part in the whole thing. So in any case, we can define and compute this invariance in this way. A priori, this will depend on equivariant variables, but it's actually a theorem that it's just a rational number. And it's important to use this smaller torus, because if you do it for this torus, then it will depend on equivariant variables. Okay, and then we can form two types of generating function. One type is you sum, you fix genus and sum over degrees. You can also fix a degree and sum over genus. So maybe let me write this depends on Q, and this depends on lambda. Okay, and then degree is a curve class. So you consider there's no mark point now, and this is yes.
You consider a multiple of this fixed class?
I consider moduli of, actually before, so this is the moduli space of stable maps where the domain is a arithmetic curve of genus G with possible nodal singularities. And so the map is stable in the sense that the automorphism group is finite. And then this is the class. So we fix the curve class and the arithmetic genus of the domain.
D is D times a fixed class because you are summing over D.
That's good.
What?
No. That's like a different concept.
Oh, so
Q to a class, right? So
oh, sorry. Is there some mistake here? This is. Yeah, this is some formal variable. Yeah, so if this has higher rank, you need several variables. So this now is just some formal variables. Okay, so yeah, so the
completion of the semi-group ring along the Cohen's curve.
Okay, you are summing over the cone.
Yeah.
But the curve is assumed to be common, yeah?
the
curve is common, C. The curve C is common, yeah?
yeah, it's a projective curve. Yeah. Yes, and
In a non-common direction, you can have no curves.
if Sorry, what is the question?
Just imagine for whom I
I think this worries, for example, tell me what's happening if your target is C3.
Is C3, so yeah, if it's C3, then the degree, H2C3 is zero-dimensional space. So then in this case, FG is just a number.
For some people, it does not have much meaning.
Yeah. so I mean, why? Like, I think it's right. Okay. So sorry. So then there's so we consider the open. So open part. So we consider L in X. So this is. Yeah, we want to consider a special kind of Lagrangian submanifolds introduced by Agnagic and Vafa. They have the nice properties that if you consider the compact maximum compact subtorus of this Calabi-Yau torus, then this preserves this. So it preserves the whole moduli problem. And then you can form moduli problem as this. You can consider it's not the fiber of moment map. The topological type is this. It's not the compact 3 torus. Okay, so this is a topological type, and actually it's in the C3 case it's Harvey-Lawson special Lagrangian. So domain, you can have border Riemann surface. I'll just draw the case where the domain is smooth with G handles and N boundary circles. And then, what? Yeah, so the thing is we want to do the open version of this, right? So now this is the map U, and it's mapped to the target such that this is holomorphic to X, and the boundary circles are mapped to L. So here we have genus, and now there are like more discrete data because we can consider. So now the degree should be some relative second homology class. But since L is of this is homotopic to a circle, so this is actually Z. So these mu i's are just integers. They are winding numbers. So we can use this to form a moduli space. So let's call this so with the degree and this mu. Yeah, so this n is already encoded in this mu. Okay, so then we do some like compactification of this by allowing nodal singularities, right? So the thing is, this torus actually acts on this moduli space. So we can similarly define yeah, so but now this will actually depend on the equivariant parameter. And actually, it's homogeneous of degree 0. So it's a rational function of one variable, u1, u2, where, so if I use a rational coefficient, this is a polynomial ring of two variables. So in order to get a rational number, actually, I choose some kind of framing, which is an integer. So then this is, yeah, so this rational, so then this becomes a rational number, and this rational number will depend on f. Okay, and then we can, sorry. Is it, so then we can, so now I should,
Sorry, why are you allowed to make that assumption about U2 and U1? U2 equal to F times U1?
no, I'm not allowed to make, I'm just saying that, so before, I'm just saying this is the definition of that number, of that rational number, is when I let U2 to be equal to FU1, I get a rational number depending on F, and that's the left-hand side. Okay? So now actually, so from here we know that actually,
Does it mean that you just pass through the subtorus again?
yeah, it's a one-dimensional subtorus, and F is like some kind of slope of that one-dimensional subtorus. So we know that actually this open invariant should depend on the so-called framing of this Lagrangian. In this setting, it's just specialization to a one-dimensional subtorus. So we can consider yeah, so it's before this Q, actually, there are like several variables. Number of Qs is equal to the rank of H2. And this is, and then we can also have form it in different, this is like you fix the topological type of the domain and you sum over topological type of the map. You can also fix the topological type of the map, which is given by the degree and winding numbers. Oh, this should depend on lambda. So if this is, if mu has n components, yeah, so we weight it by this. This is like when it's smooth, this is like negative Euler characteristic of the domain. Okay, so this defines this generating function of closed and open Gromov-Witten invariants. Oh yeah, thank you. Sorry for the typo. Should be summation over G. Yeah. So I should say that now these are smooth. So in the smooth case, so when we fix the topological type of so this is given by the algorithm of the topological vertex. Yeah, so the idea is any smooth toric Calabi-Yau threefold is obtained by gluing C3 charts, and this topological vertex in terms of Gromov-Witten invariants. So this is actually open Gromov-Witten invariance of C3 relative to 3 Lagrangians. So, and then now C3 has, no degree, so you can consider some, so the topological vertex is a generating function of open Gromov-Witten invariance, and it has they predict a closed formula. So this gives, like for each fixed D, this gives you a closed formula because you have an infinite sum over genus. So it turns out that so for smooth toric Calabi-Yau manifold threefold, this is equivalent to the conjecture by Molik, Nekrasov, Okonkov, Panda on the correspondence between Gromov-Witten and Donaldson-Thomas correspondence. This is their conjecture, and they prove. So this is proof for toric threefold. Actually, not only for Calabi-Yau, so this is Molik, Oblomkov, Okonkov, and Panda. So this gives you a very nice formula of this higher genus open and closed Gromov-Witten invariants of smooth toric Calabi-Yau threefold. So now for so let me just say in words, we can define similar things for 3 orbifolds. Indeed, so what needs to be modified is we now allow the domain curve close or border to have some orbifold points in the interior.
The left arrow, the left implication means that the topological vertex gives you a computation. What is the statement in the left?
Oh, so the topological vertex gives you an algorithm to effectively give you actually for each fixed degree some closed combinatorial formula. Yeah, any other questions?
What does equivalence sign means on the right-hand side?
Oh, the equivalence on the right-hand side, so there's like Gromov-Witten, Donaldson-Thomas correspondence. So in the previous talk, the generating function of Donaldson-Thomas invariants are defined. And the left-hand side is some generating function of Gromov-Witten invariants, and they are equal under some explicit change of variables.
Yeah, there's a vertex in DT theory, there's a vertex in Gromov-Witten theory, and the content of that is that the algorithms agree, the two vertexes agree, and so any Calabi-Yau threefold, toric Calabi-Yau threefold has equivalent GW.
Yeah, but what does it mean in terms of this F? Generating functions F.
Yeah, so I can write down the precise, I can write down the precise formula of the conjecture, but it will, yeah. Yeah, so maybe as Jim said, so if X is toric Calabi-Yau 3 manifold, so you have Gromov-Witten theory of X and Donaldson-Thomas theory of X. So then by localization, so this is like Gromov-Witten vertex, which on Gromov-Witten side, they count holomorphic curves mapped to C3 with boundary in this 3 Lagrangians. And we have this kind of generating function depend on lambda and depend on 3 partitions. So on Donaldson-Thomas side, you just compute ideal shift. So by localization, you compute certain monomial ideal in C3, as Jim pointed out. So I hope I can, so this Donaldson-Thomas vertex is yeah, so you fix the asymptotics, like they are 3D, so you fix 3 2D partitions. And this is a generating function of 3D partitions. Okay, so then this generating function can be expressed in terms of this generating function by some gluing formula. And then these two are, yeah, so the content of this is actually, if you can prove these two vertices are equal, then yeah, you can identify these two theory for smooth toric Calabi-Yau threefold. Okay, so are you happier?
When you say equal, does it mean that you're making some formula change of variables?
Oh, yeah, so I should say maybe it's better to say this, because not only do I need to make some change of variable looking like this, but I also need to, because these two are not in the same basis. One is in Schur function, one is in like Newton polynomial. But yeah, so there's a change which like give you an exact, like precise correspondence between these two two series of generating functions. So now we are going to, but then we would like the story to extend so it's a smooth Deligne-Mumford stacks. So this has also been defined like by Chen-Ran and Abramovich, Graeber, and Vistali, the orbifold Gromov-Witten theory. Oh, so this is, so this has been defined, and then this is, so Jim Bryan and collaborators consider this. And also, we can also do localization. Then, so this will reduce to orbifold Gromov-Witten vertex. So and this will be reduced to orbifold Donaldson-Thomas vertex. So what is the building block of this? So the building block of this is actually so G is a finite subgroup which is contained in, so we want to keep the Calabi-Yau condition, and we want to keep the torus action. Okay, so the building block is this C3 mod G instead of C3. So here, so you will have, so when you do localization on this side, you will have colored by the characters of G. So this will be, yeah, it's in this torus, so it's abelian. So this is color 3D partition. And then this, so you imagine you have the same picture, but now you have C3 mod G instead of C3. So, but, okay, so now if you want to know this correspondence, it is reduced to this case. I should say this part is like, so Dusty Ross said you can obtain this by gluing the orbifold topological vertex. But yeah, if I understand your paper correctly, so this even the statement of the correspondent is not known for general toric Calabi-Yau 3 orbifolds.
Well, dusting out proof, right? I'm pretty sure. Well,
No, he proved the case of transverse AN singularity.
yeah,
Oh, yeah, right. So I'm just saying that. So the thing is actually. So what is known? So what has been proved is the following case. We consider, so the action is weight 1 minus 1. So if you consider, so this is the Stacky quotient. So if you consider this quotient, it is the AN singularity. So there's also resolution of AN surface singularity. So the known result, so in this case, so it looks like this. So this is this part where Zm plus 1 acts trivially, and I draw it in this way, so this angle is like 2 pi over m plus 1. These are the 3 coordinate axes in this. And then so then you can put your Lagrangian on any of these 3 things. So if it's like, so this, so maybe let me just say orbifold so it is has been proved only for this type of very special kind of C3 mod G. For this, and this is Zong in the effective one-leg case, and Dusty Rose and Zong in the ineffective one-leg case, and also the two-leg case, and finally Rose did the three-leg case. So in this case, we don't have such a nice formula. So because the vertex formalism, right now we only know it works for this. So for any toric Calabi-Yau threefold, which is obtained by gluing this particular vertex, we have a nice answer. But in general, we don't.
But you're only leaving off one case, right? Just the Z2, Z2 acting? There's no other...
Yeah, but I'm just saying that this, so yeah, now I'm coming back to the remodeling conjecture finally. So in the remodeling conjecture, it actually works for any toric Calabi-Yau 3 orbifold without this kind of assumption. Yeah.
But that's very close to the general case, right? Because there's only one other group that could occur for the general case, right?
The general
Z2,
hard leptures.
Sorry, you're right. Sorry.
Yeah.
Yeah, that's right. Sorry.
Yeah. Yeah, so now we consider mirror symmetry. So actually X is a toric Calabi-Yau 3 orbifold. So then the coarse moduli space is a simplicial toric Calabi-Yau 3-fold. So it has quotient singularity defined by some Fang and Calabi-Yau. And we assume that it is semi-projective. So if you project it down to its affinization, so this will be a fine toric variety, but can be very singular. And actually under this, so this is a fine toric Calabi-Yau 3-fold, but can be very singular and is defined by a single cone, right? And this cone is it's just you take the support of this Fang. And this, because of the Calabi-Yau condition, this is actually a cone. So this is a lattice convex polytope. Yeah, and then you take the lattice point in the convex polytope. Yeah, so there's some there's some good way to parameterize this family. So this is how you obtain the equation of the mirror curve. You take this polytope, and basically this is the Laurent polynomial such that its Newton polytope is this polytope. So this is how you obtain the family of mirror curve from the toric data. Okay, and now you have this. So because we want to like, this will be some monomial in Q, and I should say the number of little q is equal to the number of big Q. But yeah, so there's a, so for now, let me just, and also this polytope defines a toric surface. So this curve has a natural compactification. Right, so this is the mirror curve, and actually the genus of the compactified mirror curve is equal to the, so let's assume in the generic case, this defines a smooth curve, and this is smooth compact Riemann surface. So this is equal to actually the number of interior lattice point. Right, actually, yes. So now, yeah, right. Yeah, so now we want to define the Eynard-Orantin invariant of this curve, and actually recall that we have this so maybe under some identification, this is TF. So then, actually, so now your C is containing so this is, so there's an embedding, and this is a projection. So then we choose F to be generic such that this is so actually in this this assumption, so the branch points yeah, actually it's better to say, so the critical set, so these are the ramification points. It turns out that this will be equal to, so this is some orbifold Chen-Ran cohomology of the toric Calabi-Yau threefold. In the smooth case, this is just the usual cohomology. So this is equal to the total dimension of this. Okay, under this assumption, so then we can define Eynard-Orantin invariance as follows. So it's defined recursively. So for 0, 1, and 0, 2, those are like unstable cases. So omega 0, 1 is 0. Omega 0, 2 is actually the fundamental bidifferential of the second kind. This B, P1, P2 is actually, let me write it here. So it's meromorphic on the compactified mirror curve, and it has a double pole along the diagonal. It's holomorphic otherwise. And there's some certain, so that doesn't uniquely characterize it. You need to normalize it using some A cycles of the compactified mirror curve. But the choice of A cycles actually depends on the choice of coordinate of the second cohomology here. So, I mean, it takes a while to explain the precise correspondence. But I just want to say, once we choose a basis of the second cohomology of X, or then we have a well-defined this kind of so-called Bergman kernel. And then you see that this is, so then you define this recursively by, so here this, so you can, yeah, you can rewrite your equation in terms of a new coordinate x hat and y, right? And then this is defined recursively using like some residue computation at the ramification points. So yeah, so I mean, so I probably won't say more about this. So in any case, you can use this to define omega gn and omega g0.
And what is phi? There is some phi in the formula.
What is?
There is some phi in the formula.
Oh yeah, thank you. So it's near the. So this is like near each branch point, you choose some antiderivative of this. So, but if you want to recover the Gromov-Witten invariance, so what you need to do is you need to take this and expand it using suitable coordinates. So let me just say that, let me just do it. So for example, so there's the following picture. This is the picture for, so this is when x is, yeah, I'm drawing a smooth case. And let's say your Lagrangian is this one, and the mirror curve is, so this L gives you this puncture, and you have this x. So near here, x hat is good coordinate. So you can actually write, expand, so this equation, the coefficient also depend on little q. Yeah, maybe let me use some other parameters. So this is actually holomorphic form on this disk with local coordinate x check, and you just take the antiderivative. So you can, in here, you can actually write it down instead of local holomorphic coordinate on a product of this disk. So this will, after subtracting this, this will become holomorphic. And then finally, this, when 2g minus 2 plus n is greater than 0, yeah, so I hope this is clear. So this omega gn, so this is meromorphic. It has pole at the branch point when one of this component, so this is P1 up to Pn. So if none of these are the ramification points, then this is holomorphic. In particular, this is holomorphic here. So then you get the holomorphic function. So now these are just, it is some power series with positive radius of convergence in variables Q and X. So now let me state what we prove, which is the statement of the conjecture. So this is yeah, so maybe let me also state the close. Yeah, so for FG, it only depends on the closed parameters.
And this applies for any group, and you were saying it applies for any order?
So any toric labial threefold. As long as the coarse moduli space is semi-projective, so it's a GIT quotient, you can do this mirror construction. Okay, so this is equal under the open, closed. Yeah, so maybe it's more convenient to write it in terms of the coordinate. So this coordinate, yeah, they are easily related by coordinate. On the second Chen-Ran cohomology of this. Yeah, sorry, so if you are smooth, in the smooth case, you only have this part. In the orbifold case, there are some twisted sectors. So, and this part comes from this subspace. Yeah, so these are explicit hypergeometric series. Yeah, that's okay. So I guess I just have enough time to tell you the statement. So yeah, so the way to prove it is just very quickly, because it has been known that the unique solution of the Eynard-Orantin topological recursion has a graph sum presentation, and we use that to obtain a graph sum formula here. And on this side, we use Giventhal's formula for total descendant Gromov-Witten invariants of equivalent Gromov-Witten theory to obtain the graph sum formula of the left-hand side. And we just need to show that the graph sum, the weight of each graph are equal. And that is actually a consequence of genus zero mirror theorem, which has been proved. Okay, thank you for your attention.